Here's a challenge for you with forces. We've got a lead weight that is sitting on a mass balance, and it's also supported by a rubber band which is connected to a frame. And if we look at the mass balance, we can see that it's currently displaying 449.53 grams. Now, with this arrangement, we can change the angle that the rubber band pulls on the lead weight. So as I do that, you can see as I keep moving it, the balance display increases. Important point to remember here is that the rubber band's length never changes while the angle of the frame is being moved. So the tension force provided by the rubber band always stays the same. So we're going to show you some measurements now, and hopefully you'll be able to use those to determine the mass of the weight. Okay, so we're going to start with a diagram of our arrangement. Here's the lead weight, here's the mass balance. We're going to assume that there's no rubber band. So in the absence of a tension force, we've got the normal contact force. This is the force provided by the mass balance acting on the lead weight. And we've also got the weight of the lead weight itself. And these two forces are equal in magnitude, opposite direction, and so they give a resultant force of 0 on the lead weight, so the lead weight's in equilibrium. We're only interested in the forces acting on the lead weight, so we're going to simplify the diagram by removing the mass balance. Both of the forces are now shown acting through the centre of gravity of the lead weight, and the mass balance has been removed. When we're only showing one body, then we call this a free body diagram. We can say that the forces are balanced, and so R equals W. We're now showing the free body diagram when the rubber band is added and is pulling vertically upwards. In this case, you can see that the tension force and the normal reaction, normal contact force, are both acting in the same direction, vertically upwards. And since the lead weight's in equilibrium, these two forces added together must give us the same value as the magnitude of the weight. If the rubber band is pulled to one side, as is the case here, then a component of the tension force acts vertically upwards. At the same time, because we're pulling to the right, this introduces a friction force, because we must have equilibrium in the horizontal direction as well. In the vertical direction, we therefore have T cos theta, which is the upward pull of the tension force, plus the normal contact force R, must be equal to the weight W. Writing this equation out again, we can then rearrange it to get the equation of a straight line. There are two variables in this equation, cos theta and R, and two constants, T and W. Here's the equation rearranged, and it's now in the form y equals mx plus c. So a graph of R against cos theta should give us a straight line with a negative gradient and with a positive intercept W. Okay, so by looking at the video coming up, you should be able to get the data to enable you to plot the graph of R against cos theta. Cos theta values only extend between 0 and 1, and the values of R can be obtained from the mass balance, because by Newton's third law, the normal contact force of the lead weight pushing down on the mass balance is the same magnitude as the force of the mass balance pushing up on the lead weight. So you've got values of R and you've got values of theta, and so you should be able to plot this graph and get the intercept, which is equal to the weight of the lead weight, and that's the aim of the task.